calling our trig identity that incorporates tangents and secants, we can solve this for tangent. And when we solve this for tangent, just a refresher, it looks like tan squared x equals, bringing the 1 to the other side, we have secant squared x minus 1. Or we could bring the tangent to the other side and have 1 equals secant squared x minus tan squared x. So those are the two other ways to write this identity. When we're talking about integrating the product of secants and tangents, we have two rules here, and these rules are pretty interchangeable. The first rule says if we have a secant and the power on the secant is even, then we save a secant squared. And so if we're saving a secant squared, then we're saving 2 of these powers, and so the rest is going to be the power minus 2, and then we're going to, which is still going to be an even power, and so we can then use this identity to convert those to tangents and then do a u sub on the tangents. The other scenario is if the power on the tangent is odd, and if the power on the tangent is odd, then we're going to save a secant and a tangent, so 1 of each. And so that's going to knock the power on the secant down by 1. It's going to knock the power on the tangent down by 1. And then we're going to go ahead and substitute out the remaining even powers of tangents to secants. And then we're going to do a u sub on those secants. So if we look at these two examples here, we have an n is even scenario. For these things. So we're looking at this right here. And if the power is even, then we're going to save a secant squared. Secant squared is really all we have here. And if you remember from your trig identities, integrating a secant squared gets you a tan squared x plus the constant of integration. That's kind of right in the front of the calculus book where all those tables are for integrating and differentiating. Here we still have an n is even scenario, so we're going to save a secant squared, and that's going to leave us with a secant squared. Let me write that a little better. It's going to leave us with a secant squared, and we're going to convert this to a 1 plus tan x. So we're going to go ahead and save one of the secant squareds and convert the rest to a 1 plus tan squared x dx. And then what we can do is we can go ahead and do the u sub on tan of x. So we're going to let u be tan of x. When we take the derivative of u with respect to x, we get secant squared x dx. Okay, so we can substitute out that secant squared. So this integral becomes secant squared x dx is going to be our du, and our 1 plus tan squared x is going to be our 1 plus u squared. So 1 plus u squared. So to integrate that, that's just a simple power rule. Integrating 1 gets you u. Integrating u squared gets you 1/3 u cubed. And then substituting back in, this is tan of x plus 1/3 tan cubed x plus c. For this example, we have the tangent to an even power. And so that is when m is even. And if we notice back in our rules here, the power of tangent doesn't matter unless it's odd. So if the power on the tangent is an even power, then we're looking at just using this this trig identity directly to get our even power of secant, and then we can go ahead and apply that rule. So we're going to go ahead and take this identity here, tangent squared x equals secant squared x minus 1. And we're going to go ahead and say that this is the integral then of secant squared x minus 1 dx. Now that we have an even power of secants, we can go ahead and apply the if n is even rule, and we just have a power of 2 here. So we know that the secant squared of x, the integral of that is just tangent x. So we're going to have, we can really split this up into secant squared x dx minus 1 dx. And so this becomes our tangent of x, and integrating 1 becomes x, and then we have our constant of integration. In looking at this expression, we have an n that is even and an m that is odd. And if we look back at these rules that we have here, n is even, m is odd, either one of these rules would apply. And so really the result is if you use this substitution or if you use this substitution, it doesn't matter. You would come up with mathematically equivalent expressions. Although the expressions are going to look really different, it's kind of the funny thing about trig expressions. They can look really different, but they can still be mathematically equivalent. We'll talk about that in a little bit. But one of the tricks to see which one you should pick, not that it matters, but just to make it as easy as possible, is looking at the size of the power. This is a power of 2 and this is a power of 5. And so that being the case, then this even power of 2, if we can get that removed completely, then we can make it more simple. So if we don't have to just take a piece of it out, we can remove the whole thing. That makes it a little more simple. And so what we're going to look at then is we're going to look at saving this even power, because we're going to save all of this. So we're going to do the if n is even rule, then we're going to save a secant squared, in this case 2x. So we're saving the whole thing. So and then we're rewriting the remaining stuff. And so that being the case, really we don't really have to rewrite it, although I'm just going to kind of rearrange this a little bit. I'm going to write it as tan to the 5th 2x secant squared 2x dx. We're saving this, which means we're substituting out this, so we're going to do a u equals tangent of 2x. And so when we take the derivative of that, we get, don't forget the chain rule here, 2 secant squared 2x dx. So that's a 1/2 du that we're looking for to substitute out our secant squared 2x dx. And so as we make these substitutions, then we have a 1/2 du, and we have a u to the 5th here. And so I'm going to go ahead and pull out the 1/2, and we're going to integrate u to the 5th du. And when we integrate u to the 5th du, we get 1/6 u to the 6th. And substituting back in, we get a tangent of 2x to the 6th power. And I'm just going to put the 6th power right there, and then plus our constant of integration, c. Just a side note, if we would do the other substitution, if we would do the if m is odd, we would get an answer that looks like 1/2 secant of 2x to the 6th power minus 1/4 secant of 2x to the 4th power plus 1/4 secant 2x squared plus c. And that is actually mathematically equivalent to this expression here. And the easiest way to tell is if we graph these on a graphing calculator and the graphs are either right on top of each other or offset vertically. then the offset is the constant of integration. And so it's a real quick way of showing the equivalence. Either one would be a correct answer. This one's a pretty difficult integration, but I will show that on a different example that you can get mathematically expressions that look really different but end up being equivalent. In this example, you might notice that we have something that doesn't resemble any of the trig identities we've used. And in dealing with ratios like that, the best thing to do is use our trig ratios and rewrite this in terms of sines and cosines to see if we can get a more simple expression. So let's deal with those trig ratios first. So we have cotangent cubed of t over cosecant of t. And so we know cotangent is cosine over sine. So it's going to be cosine cubed of t over sine cubed of t. And cosecant is 1 over sine. And so simplifying that a little bit more, we can rewrite the first expression and multiply by the reciprocal of the second expression. So the reciprocal of sine of t over 1. And then simplifying, we have cosine cubed t over sine squared t. So there's the equivalent, and you can see that these actually look significantly different, but they're mathematically equivalent. Trig functions are like that. And so we can really look at this as an integration problem of cosine cubed t over sine squared t dt. And so what we're going to do is we're going to go back to our cosine rules, right? We have an odd cosine. We're going to save a cosine and convert the rest to sine. So we're going to save a cosine. We can substitute that out later. And we're going to, that leaves us with a cosine squared t, which is 1 minus sine squared t over sine squared t dt. And then we can go ahead and substitute this out. We'll let u equal sine of t, which means the derivative of u equals cosine of t dt. And so we're going to substitute out that cosine of t. And so we have an integral then that looks like 1 minus u squared over u squared du. And then I'm going to split this into two fractions. So we have a 1 over u squared minus 1 du. And so there's what we have to integrate that. There's the expression that we have to integrate. So just a reminder that 1 over u squared is u to the minus 2. So we had to integrate that. And then we've got to integrate 1. That's not so tough. So using the power rule, we get minus 1 u to the minus 1. And here we get u. So we're looking at minus 1 over u minus u. And then substituting back in. U is sine of t. So we have minus 1 over sine t minus sine t plus c, constant of integration. And it's really likely that you're going to see this expression in the back of the book if you're looking at answers. This is going to be minus cosecant of t. They'll use trig identities to rewrite it so that it's only on one line. So you'll see an answer that looks like that. Integral, we see that we again have the scenario where we can have if if m is odd, or we can have the if n is even scenario, and it fits both scenarios. And like I said, when that happens, you can use either method. One method's going to be easier than the other. These two methods actually are pretty similar, so pretty simple. So we're going to go through both of them. And we're going to get very different looking expressions, but those expressions are going to be mathematically equal to each other. And we'll prove that using a graphing calculator in just a second. So at the end of these two problems. So let me kind of get this set up here. So if m is odd, then we're going to save a secant tangent. So we're going to go ahead and save a secant x tan x, and then we convert the rest to secant. Okay, so when we rewrite this, then if we save a secant tangent, that's going to leave us secant cubed x times secant x tan x dx. And so, as you can see, if we save a secant tangent, the rest are already in terms of secant, so we don't have to do any conversion, so to speak. So we're going to let u equal secant x, and we're going to let du equal the derivative of that, which is secant x tan x dx. So this integral then becomes u cubed du, and when we integrate that, we end up getting 1/4 u to the 4th, and our u is secant x, so it'll be 1/4 secant x to the 4th power plus c. Okay, and let's go and use the other rule if n is even. So, like I mentioned, either rule applies, and so we should get equivalent expressions. So in this case, if n is even, and it is, n is 4, so we have n equal to 4 here. We're going to go ahead then and save a secant squared, and then we're going to go ahead and convert rest to tangent. Okay, and so if we rewrite this, then this is looking at, if we save a secant squared, we're looking at secant squared x times secant squared x, those are remaining powers, tan x dx. Okay, and we're going to convert the rest of these secants to tangents using our identity. So we have secant squared x, and this secant squared x is going to become a 1 plus tan squared x times a tan x, because we had one there to begin with, dx. Okay, and now we're going to go ahead and do our u sub. So we're going to go ahead and let u equal tan x, and when we take the derivative of u, we're going to get secant squared x dx. So we can sub out our secant squared x dx. So we're looking at 1 plus u squared times u du. And distributing, and then we can integrate, gets us u plus u cubed du. And integrating that gets us 1/2 u squared plus 1/4 u to the 4th. And then substituting back in, for u, substituting that tan x back in, we get 1/2 tan x squared plus 1/4 tan x to the 4th plus our constant of integration. So looking at these two expressions, they look very different, but they actually are mathematically equal, and we're going to show that by graphing both of these on a graphing calculator and showing that they are in fact equivalent. Now our graphing calculators can only graph sine, cosine, and tangent, which means we have to rewrite this. So secant is the same as 1 over cosine, so this is really 1/4 times 1 over cosine x to the 4th power. Plus c. And of course, in our graphing calculators, we're not going to put the constant of integration in, which is why they might be offset. So looking at this graphically, on a graphing calculator, if we open up that graphing calculator, actually, I bet I can't do that. Okay, if we open up that graphing calculator, And I should have them already graphed in there. There we go. Okay, so if we look at the graph, if we look at the graphing calculator, I'm going to go ahead and put this in. So that's 0.25 divided by, let's clear that up. So that's 1 divided by the quantity, 4 times cosine x. And now I've got to get that to the 4th power. So I actually need another set of brackets in there. So there's my second set of brackets. Now I can take that to the 4th power, caret 4, and close up those brackets. So there is what that looks like. So there is 1 over 4 cosine, 1 over 4 secant to the 4th power. Okay, and like I said, the constant of integration here is just going to shift this thing vertically. And so all we have to do is we have to look for either something that lays right on top of this or is shifted vertically, and we know that we have equivalent expressions. So there's 1/4 secant to the 4th x. Now I'm going to go ahead and put this into the graphing calculator. So down here in y2, I'm going to go ahead and put in 0.5 tan, so times tangent of x, and I have to square that. So I'm going to come back here and insert a brackets, and come over here and put in a bracket and square that, and then I'm going to add to that plus 0.25 times, and I'm going to set my bracket up ahead of time this time, tangent of x to the 4th power. There we go. And then I can go ahead and graph this, and I'm going to change this to a thick line so that we can see it graph separately. So here's the thick line coming up, and as you can see, that 1/2 tan squared x plus 1/4 tan to the 4th power x lies right on top of my original function that I put in for y1, which means it lies right on top of this 1/4 secant to the 4th x. So they're one and the same, even though they look very different. They are mathematically equivalent, which means there's 2 right answers, which is kind of nice.